So previously we learned about alpha, beta, and gamma decay or emissions, and those were the first. They have kind of consistent names. Those are the first types of decay that were observed by people or figured out. They didn't know what they were. They just knew there were three types. They called them alpha, beta, and gamma. And those were the traditional ones. And we'll see at the end here why those were the ones people could figure out. Positron emission and electron capture are what we want to take a look at now, which is a little more complicated. They're harder to figure out what's going on. And so we only learned that they existed once we figured out kind of what was going on in nuclear processes, right? We figured out what a nucleus was because of alpha, beta, and gamma emission. All right, so positron decay involves the emission of what is called a positron from a nucleus. Okay, so a positron is a special kind of particle. And you think about the name, if we look at it, posit and tron. So tron is just like electron, neutron, proton, it's just a particle. And this is posit, like positive. So a positron, which we'll talk about a little more here, is just like an electron, but it's positively charged. And so the notation we use for it matches the notation, either the beta notation or the little e notation that we use for electrons. It has the same zero charge, but it has a plus zero mass, but a +1 charge. So in positron emission, this works just like the other decay types, where you start with a parent nuclide, you make a daughter nuclide, and then there is the emitted particle, and the total mass all balances out, and the total charge all balances out. Just like with beta decay, in positron decay, positron emission, the total mass doesn't change. What changes is the relative numbers of protons and neutrons. All right, so these positrons. A positron is a type of particle that is an anti-electron. Okay? And so what that means is it has all the exact same properties as an electron, except it is positively charged. Okay? And the mechanism that's in the nucleus for how positron decay works is similar in idea to beta emission, except it's just kind of in reverse. You start with a proton that's in the nucleus. That proton undergoes a similar process. Those quarks and funny business get involved. You then produce a neutron that stays in the nucleus and a positron that leaves the nucleus. Okay, so the particle in the nucleus was a proton. It has become a neutron. And again, you can see that for these setups, the mass is conserved or equal, and the charge is also balanced, right? Those things are balanced. You started, basically, you had one particle, the proton had one mass and one positive charge, and basically you broke that up into two particles. One, the neutron still has the mass, and then the positron has that positive charge. All right, so this positron leaves the nucleus. A positron, if we remember, is an anti-electron. That anti refers to it as it is antimatter. So what that means by antimatter is when an electron collides with this antiparticle, this positron, when they interact with each other, if they make contact, they will undergo a process called annihilation. So in annihilation, these two particles, the electron and proton, combine and they become pure energy, right? Remember that gamma is just energy. It has zero mass and zero charge. It is just pure energy. So you started with mass, you had matter and antimatter. When they combine, when they collide, they annihilate each other, which means that they destroy each other. That mass is now gone. It has turned into pure energy. The amount of energy, E equals mc squared, it's related to that. So the mass is then converted into how much energy comes out of it. And so from the kind of perspective of outside the atom, the positron will not escape the atom because a nucleus is surrounded by electrons. So a positron will inevitably meet one of those electrons and annihilate, and then you would just see that gamma radiation, that photon that comes out. So functionally, you have, say, an unstable parent. It undergoes positron decay. You make the daughter nucleus, and then this positron leaves. Okay? A positron is positively charged. It is leaving the nucleus, going out. So by random chance, it could collide with any of the numerous electrons around that nucleus. Plus, they are oppositely charged, so they are attracted to each other. So a proton and a positron, the positron will inevitably collide. It will not escape the atom. It'll annihilate with an electron, and all that comes out is these gamma radiation. And actually, the gamma radiation comes out in particular ways. They are what are called anti-parallel, which means they point in perfectly opposite directions. So these two gamma rays come out in perfectly opposite directions. And then you can figure out exactly where that corresponds to that kind of that center point. They shoot out in opposite directions. So initially, this is why people couldn't figure out that positrons were being emitted, because this just looks like gamma radiation. If you are just on the outside of the atom, you would just see gamma rays come out. And so it looks like gamma emission. So we thought that was the same idea. It's hard. You have to know what's going on in the nucleus. So positron emission, it's a little nutty, but we can use the same ideas we had before to predict daughter nuclides. All right, we can still predict daughter nuclides that come from that positron decay from positron emission. When we're doing it, same idea. We're going to start by asking, what is the starting nucleus? In this case, it's nitrogen 13 because we want products, so we want to know what the reactant is. What are the weight and mass of the particle being emitted? Well, we're told it's positron decay, so it's going to be a positron, 0 mass plus 1 charge. And then balance it. Okay. So, all right, so we're going to start with our parent. We know that we're trying to come up with a daughter, so our parent is nitrogen 13. Again, you don't need to memorize any information about atomic numbers. You can look it up if you want to know that nitrogen is 7. Decay process is positron, so that's going to be a product positron. So our arrow, then we see the positron over there. Don't know when it comes to positrons, we use the E because it is just very similar, it has all the same properties of an electron except the charge. And that's why positrons are one of the only cases where we explicitly include that positive one. Normally we would just say 1, but with electrons, we do put the positive, because just like we put a negative for the electron, we put the positive, that +1, to denote that it is a positron that we are dealing with. So then it just becomes a matter of balancing. The mass, we started with 13, and the positron is 0. So we end up with 13 for the mass of the daughter. Positron decay is just like beta emission. The total mass doesn't change. So then for our charge, we started with 7. We've lost a positive charge. So we lost +1, which means there is 6 that is left over in the nucleus. So we put those together. We can look it up. 6 is carbon. So our daughter nuclide is going to be carbon 13. So we can follow the same process, balancing mass, balancing charge, to figure out what our daughter is, the daughter nuclide for this particular process. All right, so the fifth and final type of decay process is then called electron capture. So electron capture, as the name implies, you'll note it is not an emission. This is a unique process where no matter is emitted by the nucleus. Instead, an electron from the atom interacts with the nucleus and basically gets captured by the nucleus. So we can see in this description, we have an electron, that'd be a free electron that reacts with a nucleus to combine into just a nucleus. So there is no electron product, there's no particles that are emitted from the nucleus. And so the underlying process that's going on is that electron combines with a proton to turn into a neutron. This is actually literally the reverse process of beta emission, right? In beta emission, a neutron that was in the nucleus turned into a proton and emitted an electron. Well, just like all chemical processes are reversible, you can have, equilibrium. Same thing for nuclear processes. If a neutron can turn into a proton and electron, then a proton and electron can turn into a neutron. And in this case, the neutron does just stay in the nucleus where the proton originally was. And so how this happens is, it's like those 1s electrons. Whatever electrons are, say, close to the nucleus, they get just a little too close and they get kind of swallowed up, right? So in this case, you had, this would be a proton. It combines with that electron and turns into a neutron, right? So the nucleus has changed. You don't change, again, the total number of things in the nucleus. Protons plus neutrons is the same. You've just changed what one of those things is. Instead of being a proton, it is now a neutron. So you've lost a proton, turned it into a neutron. So what ends up happening here, what this looks like from outside, right? How do we figure this out? You can't see an electron getting absorbed. And so what ends up happening is there is a space. That electron was, say, in like the 1s orbital, it's now gone. Okay? And so what can happen is electrons that are still in the atom could go into that lower energy state, right? That electron that was close to the nucleus is very low in energy, right? If you think about Aufbau principle, filling up your shells, that's the lowest energy one. That's the first place electron would go. So electrons that are in higher energy states will fall down into that energy. And it's a really big gap. So this is similar to the idea that if you heat up an atom, the electrons get excited, they fall and release potentially pretty colors of light. In this case, those energy is quite high. Those energy differences are quite high, and the photons correspond to X-ray wavelengths. So the atom doesn't emit, the nucleus doesn't emit any mass. There's no matter coming out of that nucleus. You take in that electron. But the signature for this to happen is X-ray radiation. And so if you have a nuclear process that has X-ray radiation associated with it, that's how we know it's electron capture. Again, that's why we didn't figure this one out. This is why this doesn't get like delta process or delta radiation, because we just thought that X-rays were one of the types of radiation that was coming out of the nucleus. Instead, it's a secondary effect that you can be on the lookout for. So chromium-51 decays via electron capture. Identify the product formed in this process. Okay, so still do the same idea. We're doing decay via electron capture. What's the starting nucleus? It's chromium-51. What are the weight and mass of the particle being emitted? That's what we normally ask. We do want to be careful, though, because this is electron capture. Whenever we see that capture, it is going to be different. This is not beta emission. The electron is not, the free electron is not on the product side. It's going to be on the reactant side. Balancing is all still going to work in the same way, though. Just fill out what is the necessary daughter for that parent decaying via electron capture. Okay, chromium-51, atomic number 24, found that on the periodic table. So we have 24, chromium-51. It's going to decay via electron capture, which means, again, it's a reactant. So the electron is on my reactant side. Okay, so I have chromium plus an electron on the reactant side. And then I want to figure out what the product is going to be. I need to just balance mass. It's going to be the 51 plus the 0. No mass goes in, so the mass of the daughter will be 51. Balance my charge, 24 and -1. Add those together, and I'm going to get 23. So I'm going to have a mass of 51. It doesn't change in electron capture. And then I'm also going to have an atomic number of 23. I can look it up. That is vanadium. So when chromium-51 undergoes electron capture, it becomes vanadium-51. That is the product formed in this process. Participation 417, question 3. Cobalt-59 is produced via electron capture. What was the parent nuclide? This is the third question on participation 417, due Friday, April 17th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, cobalt-59 is produced via electron capture. What was the parent nuclide? And that is it for our different types of decay processes. There are 5 different types of decay processes. Alpha, beta, and gamma emission. Those were the initial ones that were figured out because those were the unique types of particles that could be potentially emitted from the nucleus. Gamma is not really a particle, you just call it gamma ray because it is a photon, it is pure energy. Positron emission and electron capture happen just as much, but they are harder to figure out because the actual process, the actual particles involved don't make it out of the nucleus. So they're harder to figure out what was going on. The positron can't escape because it annihilates, and in electron capture, it's in the reactant side. So there's nothing even to escape. do also want to point out that when we look, one of the ways that we want to characterize all of these, the reason why there are different processes is that they cause different changes in the overall atom, right? They cause different changes in mass and charge. And one of the things that we want to point out is if we look at how we characterize these, you will note that positron emission and electron capture have the exact same effect. They both don't change the mass and they decrease the charge by 1. Either a proton becomes a neutron and emits the positron, or the proton combined with an electron to become a neutron. So in the nucleus, it's a proton becoming a neutron in both those. Even though the associated particles, different positrons, electrons, it's the same idea that you functionally find out. So important thing to note this. We want to get comfortable knowing what these are, so what the 5 are, and then also the associated radiations and changes, being able to predict all of those.
All right, that is it. 3 questions on participation 417. You want to find all 3 of those questions, get them answered, and get those answers submitted over on Blackboard. Week 13 homework will be due Saturday. Lab Group 3 evaluation due Sunday. I'll get your tests graded. Next week, we'll be back to a normal schedule for lecture, but we'll be doing lab technique presentations. So if you're not doing those, you don't need to come. And the following week we'll have the lab final, and then it'll be the end of the class. We're getting close to the end very quickly. If you have any questions about anything, let me know. Otherwise, enjoy the rest of your weekend. Yeah, there's the answers for participation go live Friday. Otherwise, enjoy your weekend. I'll see you around. Bye-bye.